Okay, everybody, let me find where we are here. All right, here we go. So this is Wednesday. So Wednesday, week 4, lecture. And what we're going to be going over today is we're going to be going over the stuff that's in the week 4 lecture here. So if I open up the week 4 section, then I have, let's see here. I posted an old recording for Monday that covers basically sections 4.1 and 4.2, I think, um, roughly that. And so today, what we're going to be doing is we're going to be looking at um, the stuff later on in that section. Okay, so that's what we're going to be doing. Let's go back to modules. Let's hope that, yeah, okay, the date's correct there now, which it was not previously. So what we are going to be doing today is that week 4 zyBooks stuff. All right, starting at around 4.2 into 4.2, 4.3 to wherever. All right, that's the plan. Also, be aware that there is a lab 3 that's posted, and that's due next week, next Wednesday. You can see that, and if you go in there, then there it is, and there's also a video to go along with it, and that should cover the whole thing. So if you follow along, you should be good as far as the lab goes. And yeah, I think that's about it. So let's just go ahead and get into this. So we'll open up the zyBook stuff, close some of these other links here. And yeah, so what have we got to say? So there's a scientific notation. We should have gone over that in the previous um, lecture, so I'm not going to go over it now. Constant variables. Constant variables, I don't really have a lot to say about either. Constants, um, just the main point of a constant is that it's a variable where once you set the value, you will never change it. And you use them in places where, uh, well, where you know, first of all, that you never will want to change it, but also you use them in cases where the user needs to know that it's not going to change, and the compiler knows that it's not going to change. And so sometimes the compiler can generate faster running code if it knows that the value will never possibly change. Um, yeah, so code can be a little bit faster if it knows that. So the way you do it is, as it says here, you just use the word final in front of whatever it is, right? So you can do like an int x, right, equals 5, for example. You could do a double, y equals 2.3, for example. And if you want them to be constants, so these are just variables. And if you want them to be constants, then it would just be final int x equals 5. That's it. Final double y equals 2.3. Right? So you just add the word final in front of them, and then they're constants. The notation, not notation, but what zyBooks does is it will name them all capitals, and then you know if it's a constant or not. So whenever you see all capitals, like seconds per hour and speed of sound, then you know it's a constant, and that's about it. Okay, so there's not really a lot to say about that. Um, yeah, there's not really a lot to say about that. So we'll move on. So we'll pick up here. which is going to be section 4.3, which is math methods. And so the idea here is pretty simple. Um, there are common math functions that you need, or you want anyway. So math functions that you want to use sometimes. Examples of what those are would be things like, exponents slash powers, right? Um, that's one thing you'll need. Square roots, that's another thing. Technically, a square root is an exponent, but usually we think of them differently. Um, what else is there? There are things like absolute value as well. That's something you need. Also, what else do we need other than absolute value, square roots, and exponents? Well, those cover a lot of things, but there's also logarithms. You could use a logarithm. Um, Also, there's the exponential function, which is not the same as power, because an exponential function specifically is the one that's e to the x, right? Not just any number. It's the special number e. Also, what else can we think of? The trig functions. Trig functions like sine, cosine, tangent, secant, cosecant, cotangent, all those. Inverse, trig functions, etc. Right? So there's more. There's more of these. There's like a whole bunch of them. Okay. And the thing that you have to know is that these functions are not hidden from you, but they're accessed through a math library or a math class. So you access them through the math class. So when you want an exponent, or not an exponent, let me do something else. So like if you want a square root, so if you want a square root, for example, it's not this. It's not SQRT, which in some programming languages it would be. It's not square root x like that. In Java, you use capital M math dot square root x. Okay, so it's not square root, it's math dot square root, because the function or method square root lives inside of the math class. And so you just have to know that that's how you access them. So whenever you want a square root, you have to type all of this, math dot square root. Okay, so all of these functions have are accessed in a similar way. All math methods in a similar way. So if you want to do a power, like if you're trying to do like x to the y power, that's exponent. How do you do it? You do it this way. Math dot pow, and then x comma y. That's how you do it, right? If we want a square root x, can't really write it another way. How do you access it? You do it with math dot square root x. I messed that up. Let me fix it. What else is up here? An absolute value. How do you think you do an absolute value? Absolute value. How do you do it? You say capital M on the math dot ABS. ABS is an absolute value, right? How you do a logarithm? You do math dot log x. Now that would be the natural logarithm actually, would be math.logx. Not ln, by the way. You probably use ln for natural logarithm in your math classes, but not in programming. In programming, the natural logarithm is almost always just log. And if you want like the log base 10, normally log base 10 is log in math. But in computer science, usually if you want a log base 10, it's usually called log 10. And there's always a log base 2 because computers are used to using base 2 binary arithmetic, and that's usually log 2. So we have these kinds of functions, and there's going to be a list of them down here, which actually maybe maybe I'm typing too many of them here. Um, yeah, I guess I kind of have kind of doing too much here. But if you're curious, you can always go to um, the Java math class and access them that way. Um, what am I doing? Okay, yeah. So Java math class methods. There we go. Sorry about that. Java math example 1. Let's see here. Just looking for a list of them. So we have math.square root, math.pow, math.log, math.log10. They have a special one for log of 1 plus x, uh, and then a special one for math.exp. So we just have a lot of these methods. So I don't know. They exist. They're there, and we can access them. So with that said, let's go ahead and see if we can use them for calculations. Okay. Let's go through this here. So specifically, we're going to be looking at square roots and powers and absolute values. Okay. So you should know how these all work in math, right? Like the square root of 9 is 3. 6 to the power 2, 6 squared is 36. And the absolute value just takes whatever the number is and it makes it positive. So if it was negative, it's now positive. Okay, and then they list some more of them. Log, which is natural log, log 10, exp, ceil, and floor. So ceil is round up to the next number, which, I mean, like for example, here's math dot ceil. So if I do like 4.2, for example, what is math.ceil 4.2? Well, it rounds, but it only rounds up. It doesn't round to the nearest number. It will always round up to, in this case, 5. Oops, not 65. 5. Okay, so that's what ceiling would do, is round up. The floor, math.floor 4.2, will always round down. So it'll be 4.0, right? So ceil always rounds up and floor always rounds down. Ceil is for ceiling, right? So that's called the ceiling function, which is why it's up, right? The ceiling is above you. All right. So anyway, at first they're just going to make sure that we understand what these functions are doing. And so you just make sure we understand the math. So like math dot square root 36, that's just the square root of 36, which is 6. Math dot square root 81, square root of 81 is 9. Math dot pow 8, you need to understand that that is 2 to the power 8 like that, which you can grab a calculator and figure that out. It's 256. Yeah, again, notice that you have to use a comma between the 2 and the 8 there. That's how it's done. Is this valid? Square root 2 comma 8? No, right? This is not valid. You take the square root of one number. You don't take the square root of two numbers. So this doesn't make sense. Okay. Now what about math.pow of 8? That also doesn't make sense, right? You can't do a power with only one number. You need two numbers, right? X to the Y or 2 to the something. So you need a second argument there. So this is not valid. If W and X are doubles, is this valid? Math.pow WX. Sure, right? That's how you're supposed to use it. Two arguments. What is Y? So this is just kind of seeing if we can trace our way through the code a little bit. So the way I would work this out is something like this. So if you've got W equals 3.0, and then you've got this line, I would do this. So I look at the second line and it says math.pow W. Well, the W is 3.0. So I would take the W down here and change the W to 3.0 like that. This is how I would do it. And then I look at the second line again and I see that there's a 3 plus 1. So I would do 3 plus 1 is 4. And then finally, I've got a math.pow 4 to the 2. So that is a 4 to the 2 power. And 4 squared is 16. So the answer is 16. Okay, so you just trace it through step by step. All right. So there's not really a lot to say here. I'm not going to work through this example. Um, maybe I will a little bit. Well, I mean, I don't think so. So again, they're trying to see if we can understand the math involved. So they're giving us this equation here, this equation. And then they give us a bunch of numbers. So if I fill them all in, we should be able to work this out. So like the first thing here says if mass, so that's like initial mass is 10.0. So over here, I'm just going to find initial mass and I'm going to replace it with 10. So I see it right here. Initial mass is supposed to be 10.0, so I'll put in 10.0. And then I've got growth rate is 1.0. So I look for the growth rate. I see it right here. Growth rate is 1.0. And then I see years grow is 3. So I see years grow right here, and that's supposed to be 3. 3. Okay. So I do that, and then again, I'm still going to keep working it out. So the next thing I can do here is I see that there's a 1 plus 1, 1.0 plus 1.0. 1.0 plus 1.0 is 2.0, 2.0, like that. And then finally, this right here, the part that I've highlighted, is 2 to the power 3. So that's 2 times 2 times 2, or 2 to the third power. 2 times 2 times 2 is 8. So this exponent here, this power, is 8, 8.0. So I'll replace that with 8.0. And then finally, I've got 10 times 8. So 10 times 8 is 80. So the final mass is 80 when it's all done. Okay, and then if you look, they worked it out just exactly the way that I did. Okay, so we have more of these that are about to talking about how to evaluate these. So this is kind of weird, this one. Maybe we'll just do it because it's weird. So they've got this, right? X equals square root y squared plus z squared, and they're doing it in several lines instead of just in one line. So just imagine this, okay? If you wanted to calculate this and you were going to take several lines, Um, you could calculate it step by step. So if you wanted to calculate this, one way to do it would be to calculate y squared first, and then calculate z squared first or second, and then add these together, y squared plus z squared. And then after you add y squared plus z squared, you could take the square root, right? That would be okay. And so basically what they're doing here is this step by step. So they're saying one way to do this would be to take and calculate this first thing. And so they make a temporary variable called temp1, just a variable name. And they're saying that's where we're going to calculate y squared. Now, most people would just calculate y squared this way. If they were writing Java code, they would just write y times y. That's an easy way to do it. But for whatever reason, they're using MathPow. So math.pow, how would you calculate the y squared? It would be y comma 2, right? So we're looking for this. That's the first thing they're going to do. So they're saying that's one way to do it. Do that first. And why are we doing the y squared before the z squared? Because right below this, it says, for this exercise, calculate y squared before z squared. So we did. Okay, so that's the first thing. Now, after you calculate the y squared, we could calculate the z squared. So we'll calculate the z squared the same way, but we'll give it a different name. We'll call it temp2. Math.pow and z comma 2.0, right? That could be the second thing we did. Okay, now the third thing, I guess we're combining combining a couple things here, is we want to do, they want to add these together and take the square root. So if you wanted to add y squared plus z squared, then we would actually need to add up temp1 and temp2, right? Because temp1 is x squared, sorry, temp1 is y squared, and temp2 is z squared. So if we take temp1 and we add it to temp2, that's the inside here, y squared plus z squared. And then in order to take the square root of that, it would be math dot square root, like that. That would be the square root of y squared plus z squared. And then if we're supposed to set it equal to x, it would be x equals. Okay, so why are they doing it in 3 lines? I don't know, but they are, and they want us to figure out what they should be. So I think this is the way. So once we figured out a way to do it, then we should just find the answers over here. So the first one is math.pow y and 2. So that's the third one here, correct? The second one is temp2 equals math.pow z and 2. So we look for the z and the 2. There we go. And then for the third statement, we're looking for x equals math square root. And then we want the temp1 and the temp2 both inside of the square root, because here, right, they're both inside the square root. So we're looking for the right one, and it looks like the third one looks right. Okay? All right. Now, what they're trying to show you in the next activity is that you can put math functions inside of math functions, and the compiler will just figure it out. Okay, so like for example, on this previous one that um, we did it in 3 lines, right? But we could have done it this way. We could have said math dot square root, because we had a square root on the outside. Looking at this one again. And then what's inside the square root, and maybe I would actually do this, put both parentheses for the square root. And then what's inside the square root? Well, we have a y squared, right? So how would I do y squared? I would go math dot pow y comma 2.0. That's the square, that's y squared. And then I would do plus, and then we need z squared, which is math dot pow z comma 2.0. like that. So like this one line here replaces these three lines. Okay. And the fact that you can put a math function inside of a math function is what they want you to understand down here. Um, and so that's what they're doing. So they're showing you an example of that. All right. Now we should be able to work this out as well. So like if I take one of these, we should be able to work it out from the inside out. So you just take a piece by piece, working from the inside out. So work out from inside out. Okay. So what that would look like is we take math.pow 2 comma 3. That's 2 to the third power. 2 times 2 times 2. So 2 to the third power is 8. So all this highlighted code could be 8. And then now you've got math.pow 2 comma 8. That's 2 to the 8th power. Again, use a calculator for these. So like use like Wolfram Alpha or something. If you don't know this website, now you do. You can go 2 to the 8th that way and get 256. You can hit enter if you need to and get more results. So math.pow 2 comma 8, 2 to the 8th power is 256. So this one is 256. And I could have put 0.0, but I didn't. So, you can do any of these that way, work them out from the inside out. So like this one, x is -9. So on the second line, you put the -9 in for x. Then you've got the absolute value of -9. Absolute value of -9 is +9. And then you've got the square root of 9. So the square root of 9 is 3. So that one's 3.0. Okay, so you just do them in order and they'll work out. So let's try these challenge activities and see how they go. I don't know if I'm going to do all of them, but I'll do some of them. And let's see how it goes. What we're doing here is typing the program's output. So basically what we just did. Also, keep in mind that they've got this printf stuff, which I think we did in the previous lecture or the one before it, where we talk about the you can print it out rounded to 1 decimal place or 2 decimal places, etc., based on how you write that. All right, let's try this. So, following this code, so we've got double x, and then x is the square root of 49. Okay, so when you get this line here, you say, okay, x is the square root of 49, but the square root of 49 is just 7, right? So it's really just 7. And then it prints it out. So when we print this out, remember how this is going to go. So this right here means we're printing a floating point number, a decimal number. That's what the F is for. The 0.1 means rounded to 1 decimal place. Okay, so we're rounding to 1 decimal place, and then the backslash n means new line. So we're supposed to print 7.0 in place of this and round it to 1 decimal place. So if you round 7.0 to 1 decimal place, it is 7.0. And after that, the backslash n is a new line, and so you hit enter, and this is what they want. Okay, so that's correct. Next. So same thing here. We've got this time something slightly different. So we have, oops, not what I wanted. Math.abs 1.3. So ABS is absolute value. So the absolute value of 1.3 or negative 1.3, sorry, the absolute value of negative 1.3 is positive 1.3. So we have 1.3 We look at what we're printing and it says this will output 1 decimal place. So we're rounding this to 1 decimal place. Well, guess what? It already is. So 1.3, and again, there's a new line afterwards because of the backslash in there. Okay, so keep going. It's all the same type of thing. We have math.pow. So that's 5 to the third power. So if you don't know what that is, you get a calculator and you go 5 to the third power. It's 125. So we know that this is going to be 125. And we are rounding it again to 1 decimal place. So when we type it in, it's 125, but rounded to 1 decimal place, you have to put 0.0. Enter. Okay. Uh, Again, they're not super complicated here. So what would you do here? You would have to take these two numbers, add them together. I'm not going to bother doing that in my head. I'm just going to type them in. So negative 7.1 is the result. So this is negative 7.1. And then I have the absolute value of negative 7.1, which is positive 7.1. So we go 7.1, enter. All right. So slightly more complicated here. We have to work this out from the inside out. So inside out, math dot square root 9. Square root of 9 is 3. And now we have 4 raised to the power 3. 4 times 4 times 4, which again, you can use a calculator for it, but it is 64. And looking here, this is rounded to 1 decimal place again. So this is just 64.0. Enter, and that should be correct. Okay, so that's all you're doing on these. You might have slightly different ones than I have. All right. Now we have to write them ourselves, and we got 3 of them. So this is just seeing if we can remember or use the methods from the math class, and we'll see if we can. But it shouldn't be that hard. So it says compute z equals, this is absolute value, x plus y. So all you're doing here is you're trying to write this as Java code. So z is the absolute value of x plus y. So you just write z equals absolute value, but to get an absolute value, it's capital M on math dot ABS, and then what's inside the ABS? X plus y, x plus y. So this is just this, right? We don't have to deal with the typing in the numbers or anything else because the lines above where we are where they read the numbers from the keyboard, and the line at the end is where they output it to the screen. So all we have to do is this one little math command. Okay, that's all they're looking for. So this will compile and we'll just make sure it works, but of course it will. And keep going. Now, as we go, you can see that they're making it harder, right? But it's not impossible. Just be careful. So we're coding this. So z equals, okay, that much is easy. I see we have another absolute value, math.abs. I'm going to put both sides of the parentheses there. What goes in the ABS? Well, we got a y and then a times, right? Asterisk is times. So a y times, so I'll type that, y times. And then we have a square root x. How do we get a square root x? That's another math function, right? It's math dot square root. So math dot sqrt x. right? So there you go. Got a couple extra spaces, but that's it. All right, and that's all it's looking for. So this one's more complicated, but we can do it. Z equals, that part's easy. Um, then we get to a square root, right? The whole thing is in a square root. So I'll type the square root now, math.sqrt, parentheses. I'll even put the semicolon on the end. Now what's inside the square root? Well, in the square root, there's an absolute value, right? Absolute value there. But actually, the absolute value is in a cube, right? That's a power 3. So what we have to actually do is we should do math.pow, right? The whole thing is now to the power 3. So I'm going to do the power 3 here, math.pow. And now remember, pow takes 2 commands, right? When you do like 4 comma 3, that means 4 to the exponent 3, right? That's what that means. I know that this is not Java, but we usually use the caret for exponents in most other things. So hopefully that makes sense. So inside the square root is a power 3. So if it's a third power, then I don't know what the first thing is in that power, but I know the second thing should be, why do I keep typing in? The second thing should be a 3.0. Okay. Now, what's the first thing? Well, what are we taking the cube of here? We're taking the cube of an absolute value. So inside math.pow, we need an absolute value. So right where the cursor is, I need math.abs. And I'll put both sides of the parentheses in. And then what's in the ABS? What's in the absolute value? What's in the absolute value is y minus x. So y minus x, like this. And you can get rid of some of the spaces. I don't know how, like they don't always get rid of the spaces. They like spaces in your textbook, but there's too many spaces is confusing, and not enough spaces is also confusing. So anyway, I typed that all up. So you have a square root on the outside, and then inside the square root you have a third power, and inside the third power you have an absolute value, and inside the absolute value you have a y minus x. But I mean, that's pretty tricky to write. All right. So then they want us to write this code. Now, pay attention to your variable names. I've noticed this in my other classes. Um, a lot of students, right, they see the formula here and they forget that when we're writing the code down here, these are our variables, right? They're all listed here. These are the variables that we have available. So like, for example, when you go to write this, you do not start by writing distance equals, right? That's wrong, because even though it says distance here, you have to actually ask yourself, well, what variable are we calling distance? And if you read, it says assign the result to points distance. And if you look at your list of variables, x1, y1, x2, y2, points distance, x distance, y distance, then there's we have these variables here. So yeah, so we could do this in one line or we can do this in 2 lines. It's kind of our choice. They didn't tell us how we had to program this. But the way that they've kind of set it up by having these two variables, x distance and y distance, you see x dist, y dist. What they're kind of trying to lead you towards is um, making x2 minus x1 x dist and making y2 minus y1 y dist to make it easier to write the whole thing, to make it a little bit shorter. So anyway, if I'm going to do this, let's try to do this. So if we're going to take 3 lines to do it, this this first part right here, x2 minus x1, I could call that x dist. Okay, so I'm going to do that. I'm going to say x capital D dist, that's the variable name, equals, and I'm going to say it is x2 minus x1. Okay, and I'm going to say that the y distance is the same thing, but for y. So y2 minus y1. Okay, so I've now calculated a little part of this. I've calculated the inside here, and I've calculated the inside here. Now what I got to do then is I've got to, first of all, square those, and also I need a square root. So to write the actual distance, which is going to be stored in this variable, points distance, it says that, what I'm going to need is, how do I do a points distance? Well, the whole thing is a square root. And I know how to get a square root. That's capital M math dot sqrt. That's a square root. Got all the space inside the square root now. What goes in there? Well, x2 minus x1 squared, x2 minus x1 squared, you could use a POW for that. So you could type it this way, math.pow, and the thing you want to square is x dist, right? Because x2 minus x1 is already calculated here. So x dist and a 2.0. So you could do it that way. MathPow x dist 2.0, perfectly okay. But what I would say is that when you've got like a second power or a third power, like a low power, rather than writing x2 minus x1 squared, or, in that case, x dist squared, it's easier just to do it this way, x dist times x dist. Isn't that the same thing as a power 2, right? We're multiplying by itself. So that's how I would do that. And then I would have plus, and then we have y2 minus y1 squared. Again, you could use the power function, or you could just say this is y dist, and to square it, it would be y dist times y dist. So y dist times y dist, like that. So to me, this looks correct and, relatively concise and relatively easy to read, right? And it calculates it and it says we're good. Okay. We'll do a little bit more of this. And this is going to be a little bit confused. Well, I won't say a little bit confusing, but it will be when we get to the remainders. But at first, it won't be. So this is section 4.4, which is integer division. And the modulo operator, which, if you're not a programmer, you probably have not heard the word modulo. But now you are. Okay, and so let's talk about it. So first of all, when you're talking about integers, so when you do integer arithmetic of any kind, there are no decimal places, right? There are no decimal places. Why? No, go away. So there are no decimal places. And so what happens is if there would be um, a decimal place, it just disappears. It just goes away. You don't round, it just goes away. So anything that would be after the decimal point, so any digits that would have been after the decimal point are just dropped off. There's no rounding or anything. They're just gone. Okay. So as an example of that, if I do like, let's say 7 over 2, right? If you do 7 divided by 2, of course, it's 3.5, right? But um, so 7 over 2 is 3.5 as a decimal. So you know that that is 3.5. That's what it would be in math, right? Real math. That's what it would be. Uh, in Java, that's not what happens. You have 7 over 2 is 3.5, but because it's an integer over an integer and we didn't do anything to say that it was not that, I don't know why I put a 0 there. Um, so 7 over 2 is 3.5. And then, but because we're doing integer over integer, there is nothing after the decimal point. So you just delete that. So in Java, with integers, 7 divided by 2 is just 3. Okay, that's just how it is. Okay, now if you use doubles, if you did 7.0 over 2.0 in Java with doubles, you would get 3.5. And that would be in Java double math. I'll say floating point math. Okay, so what this section is about is this stuff. Okay, so when we're dividing or any other operation, there are no decimal points; they just disappear. Okay, so when we're doing this, if you grab a calculator, so I'm just doing this on a pocket calculator here, but if I take a pocket calculator and I do 13 divided by 3, I get 4 and a third, which as a decimal is like 4.33333 forever. But guess what? If we are doing integer arithmetic, you just take everything after the decimal point and delete it. So 13 over 3 is just 4. Okay. Now, if you do 4 over 9, you get 4 ninths, which is 0.444, 0.4444. It keeps going. But because we're doing integer arithmetic, everything after the decimal point, delete it. So what do you get? 0. So 4 divided by 9 is 0 in Java. Okay? Now, when you do something like this, you just work it out. Um, you work out the parentheses first. So like take all this right here. We can just add that up. 5 plus 10 plus 15. 5 plus 10 is 15. 15 plus 15 is 30. So this is 30. But then you have 1 over 3. 1 over 3 is 0.3333. But we know everything after the decimal place is gone. So it's just 0. So we have 30 times 0, which is, guess what? 0. So this doesn't look like it should be 0, but it's 0. Okay? Now here they're just asking us to um, think about it. So like we have x is 10 and y is 4. So this is 10 over 4. So you grab a calculator. 10 divided by 4 is 2.5. So 2.5, but this was an integer and an integer, so delete the 0.5. 10 over 4 here. Now this is going to depend on what our variables are, so I'm looking up at the top here. Some expression only use literals to focus attention on the operator, but most practical expressions include variables. Okay. Um, Now, the way Java works is as soon as you put in a decimal point, it will assume that we're calculating floating point numbers again. So when you do 10 over 4 and you get 2.5 here, this time it will keep it because we're doing, as soon as you put in the point 0, it says, oh, I guess we're not doing integer arithmetic anymore. We're doing floating point arithmetic. We're allowed to use decimals. So it won't cut off the point 0.5. Okay. Same thing here. X is 10 and Y is 4. When you say double Y equals 4.0, that a double is a floating point number. So when you do the 10 divided by 4, you get 2.5. And because a double was involved, it will not do integer arithmetic. So as soon as a double is involved, it will do the calculation correctly. Okay? All right. So this is just about errors. You can't divide by 0 for integers. Okay. Um, Not a lot to say about it. Uh, all right, so determine the result type error if the program would terminate due to divide by 0. All right, so 100 over 2, 50, right? 100 times 1/2. Well, again, remember that this is a trick. 1 over 2 is 0.5, but we cut off the 0.5, so this is 0. So 1/2 is actually 0. So this is 0 times 100. Right? Now, if you take away the parentheses, now it'll work it out left to right. So now it's going to do 100 times 1. 100 times 1 is 100, and then 100 divided by 2 is 50. So do you see that the order that you do these operations in matter? If you do 1 divided by 2, you get 0. If you do 100 times 1, you get 100. So it depends on which one you do first. Um, okay, so evaluation is done left to right for multiplication and division. All right, here I think we're back to where we were. So, or this is an error actually. 1 over 2 is 0, and then we have 100 divided by 0, which they told us is an error. All right, and this, you just kind of have to work your way through it. So put in the numbers. So in the third line, 1 over y is 5, so 5. X is 2, 2. So you have 5 minus 2 minus 3, which is 0. And then you have 1 over 0, which is error. All right. Now, this operation here is called the modulo operator. And what it does is it gives you the remainder. So you have to remember how to do long division, which I'm actually going to Google long division real quick. So I just want to look at an example of it. I'll look for images. Um, yeah, so do you remember this? We'll look at this. So this is just an example here, right? Um, so pretend we were trying to divide 3723 by 23. And so like the way you do this mentally, well, not mentally, the way you do it, right? You have to think back to grade school. You go, how many times does 23 go into 3? And then the answer is 0. So you put a 0 there. And then you do 0 times 23 is 0, and you subtract. 3 minus 0 is 3. Bring down the 7. So you say, how many times does 23 go into 37? 1 time. So you put a 1 here. 1 times 23 is 23. And then you subtract 37 minus 23. And you get 14. And then you bring down this 2. So now you have 142. And you say, How many times does 23 go into 142? And the answer is 6. And then 6 times 23 is 138. And then you do 142 minus 138 and you get 43. Actually, no, you get, what do you get? You don't get 43. What's, huh? Oh, you get 4. They, whoever wrote this is not the math expert. The 4 should be, this 4 should be where the 3 is, and the 3 should be one space over. But you do 142 minus 138, you get 4. You bring down this 3 over here to here, so you have 43. You say, how many times does 23 go into 43? And the answer is 1. 1 times 23 is 23. 43 minus 23 is 20. And then you ask yourself, how many times does 23 go into 20? And it doesn't, right? So this is the remainder. So you could say this, like the result of this operation here, you could say that when you do 3723 divided by 23, the result is 161, right? And the remainder is 3. Or I said 3, but the remainder is not 3. The remainder is this number, the 20, right? Does that make sense? So when you do long division without decimals, you will get a remainder typically. So 3723 over 23 is 161 with remainder 20. Now, here's the thing about Java. In Java, if you do this calculation, 3723 over 23, you get 161. Okay? Because we know that you're going to drop off the decimal anyway. If you do this operation, 3723, and you put a percent there, 23, it kind of looks like division, right? How there's a slash and there's a slash. That's the modulo operator, and the answer is 20. That's the remainder. So when you use the slash operator for division, you get the division, you get the quotient. When you do the percent sign there, you get the remainder. So that's the division, and or that's actually called the quotient, I'll say, and that is the remainder. And so this is actually very useful for doing things, which is why it's an operation that we can do. Okay, so that's that operator. It means the remainder. It's also called the modulo operator. Okay, so that's what it is. And then they give you some examples. So I'm gonna do some examples here. Ignore the text. So if I do 24 over 10, right? You do that, you know that 24 divided by 10 is 2.4, right? But because we're doing integer arithmetic, you delete that. So 24 divided by 10 is 2 actually in Java. And when you do 24% 10, it's the remainder. So the way you would work it out is you would say 10 goes into 24. I'll write it down here. A 10 goes into 24 two times, right? 10 goes into 24 two times. And if you do 2 times 10, you get 20. 2 times 10 equals 20, right? So how much is left over from the 20 up to the 24 is 4, right? And that's the remainder. So 10 goes into 24 two times with remainder 4. Okay. And that's what we're doing on these calculations. Okay. Now, the thing that they use it for is actually kind of like it's very useful, but it's a little bit confusing. So like you can use the modulo operator for things like if you had seconds, like or minutes to hours and minutes, or for things like, let's say, if you had like a number of seconds to hours, minutes, seconds. Okay. And how would you do that? So I'm going to give you an example. So um, we'll look at I mean, it's the same example that's behind here, but I want to just explain one. So like, let's say we have like 555 minutes, right? And we want to write it as, you know, X hours and Y minutes, right? Like we're not good at thinking about minutes. Uh, um, so like how many minutes or how many hours is 555 minutes? I don't know. So like I'm not good at thinking about that. And so you could obviously work this out. So if I'm working this out by hand without a computer, here's what I would probably do. I would go 555 over 555 over 60, right? Um, because there's 60 hours, or sorry, 60 minutes in an hour. So I grab a calculator and I go 555 over 60. And when I do that, I get 9.25 is what I get. I get 9.25. And so when I get that, that tells me there's 9 hours there, right? So I now know. So I know that uh, we have 9 hours. 555 minutes is 9 hours and some number of minutes that I haven't calculated yet. Does that make sense? So when we do 555 over 60, we get 9.25. That's 9 hours and a quarter. Okay. So I know 555 minutes is 9 hours and some number of minutes. So then what I do is I say, okay, well, how many minutes is left over? After the 9 hours, right? And the way you could calculate it, the way you would calculate it generally is you would do this. You would say, okay, well, we have the 555 that we started with, and then we would have to subtract. We know that there's 9 hours, so we do 9 times 60 minutes per hour. And I would do this calculation, and I would get 555 minus 9 times 60. And when I do that, I get 15. Okay. And then I combine all my work here, and I would say that 555 minutes is 9 hours and 15 minutes. Okay? So hopefully that made sense. And once we've done one of these calculations, now I can show you how to do it much easier in Java. So it's easier using what's it called? The modulo operator. So here's how you do it. So pretend we have a variable. So I'm just going to type this in. I'm going to say int x. I'm going to be like total minutes is, let's just say 555. Okay. So that's the example I have, right? Now, what I'm going to do is simply this. So I'm going to have a variable. Let me just make two variables. I'm going to be like, I'm just going to call it hours and another one, and I'm just going to call it minutes. Okay. So if I want to get this same answer, 9 hours and 15 minutes, here's the calculations I would have to do. I would for hours, I would just take the minutes, which is the 555, and I would just divide by 60, right? Because that's the same as this calculation, but in Java, there's nothing past the decimal point, right? So when I do 555 over 60, I'm just going to get the 9, which is what I want. So this will just give me the 9. Okay. Now, in order to get the leftover, the 15 minutes that's left over, that's actually just the modulo. So for the minutes here, instead of that calculation that I thought about on the previous one, I just do minutes is total minutes modulo 60. And that will give the 15. And that's it. That's it. So you divide to find out how many hours, and then to get the leftover, you use the modulo, right? Leftover is a remainder. And so with this in mind, if you understand this concept, these problems are easy. But you do, I mean, they are tricky to think about because you're not used to doing this. But the modulo operator will give you the leftover after you do a division. So a lot of these problems are going to look just like this, where you see a division and then you see a modulo right after it. And it's the same thing, right? Total minutes over 60 and total minutes modulo 60. And one gives you the division and one gives you the remainder. Okay. So, oh, actually you see the exact thing I just did right here. Okay? So, they want to see if we can work this out. So, how many times does 2 go into 50? 25 times, right? Does it if it goes in evenly, there's no remainder. So that's 0. Okay. What about 51? Well, that's one more, right? So um, 51 divided by 2, 2 goes into 51 50 or 25 times. 25 times will get you to 50, and there's 1 left over, so the remainder is 1. 78 modulo 10. So 10 goes into 78 7 times, right? I'll write a couple of these just to, I hope they make sense. So 10 goes into 78 7 times, right? With remainder, well, 7 times 10 is 70, and the leftover is 8. So 7 times with remainder 8. So this is 8. All right. 596 modulo 10. Well, it's going to be 6, right? Um, this is an error because remember, 1 divided by 2 is going to be 0. And we know you're not allowed to have a 0 on the right side of a division or a um, modulo. They told us that. So this is an error. You can have a modulo, or sorry, you can have a 0 on the left though. 0 modulo anything is just 0. Um, all right. So this is going to talk us through basically this logic. Um, so it says a florist wants to create as many bunches of 12 flowers as possible. Total flowers holds the total number of flowers, right? So imagine there was like 1,000 flowers. Well, it's 10,000 flowers. Like let's say that we had this. Like imagine, right? If you wanted to know how many 12 bunches you could get, you would take the 1,000 and you would divide it by 12. That's how many bunches of 12 you can make, right? So that's what you're putting here, except you have to write it that way. You take the total flowers and you divide it by 12. That's what they want. Okay. Um, Now, using only the variable total flowers, complete the statement to assign remaining flowers. Well, we know that when you do total flowers over 12, that would be like the equivalent of this. How many hours do you get? If you want the remaining flowers, that would be this one, right? The remaining flowers would mean the leftover flowers. That's literally the remainder of flowers. So you do this one for the remainder. Parentheses matter. Yeah, of course they do. Um, okay, we're going to do this one challenge activity and then we're going to stop because we're over an hour um, into this. Oh, actually, you know what? We are well over an hour into this. I'm going to stop here and we will start here next time. And on Friday, get through the rest of the challenge exercises for this. So that's going to be it for now. I'm going to talk to you guys later. Um, yeah, I'll talk to you guys later. How do I stop? Okay, there we go.